welcome back to another class of fundamentals of particle and fluid solid processing. We will continue with our section that we started in the last class, that is the flow through packed beds and the granular material. So, we concluded that, or in fact we have seen that the laminar flow through bed of material or the objects, and what is the pressure gradient in that case, as well as when there is a turbulent flow, how we can estimate the pressure gradient across that stack of material having a mono-sized sphere particularly. Okay. So, the question was whether we can have a generic expression that irrespective of the flow regime or irrespective of the flow region, being it laminar or turbulent, whether we can use that expression. Okay. So, after several years of Darcy, Argon came up with this expression, the famous Argon equation. You already know about this thing, but let me again refresh your memory by saying that this Argon equation has two components. Okay. The first component, that is this 150 and multiplied by this part, and there is another 1.75 multiplied by this part. The point is, this part basically contributes when the flow is laminar. The pressure drop contribution, or the contribution of this first part to the overall pressure drop, is the dominant when there is a flow in laminar condition through the packed bed of material. Okay. And the other part, this part becomes dominant or contributes dominantly when the flow is turbulent. So, he has combined these two parts. It is similar, the first part is similar to the Koenig-Karman equation, but with a different the factor or the constant value, and the other part is the Burke-Plummer. So, the point here, you can see that in case of laminar flow, that means when this first part is dominant. Okay. So, when this first part is dominant, the pressure gradient increases linearly with the superficial velocity u. The del p by h is proportional to u. That was the observation that was mentioned by Darcy, and this is completely independent of the fluid density. This part has no contribution of the rho f or the fluid density. When there is a turbulent flow, the pressure gradient increases square of the superficial velocity, and in this case this part does not contain the fluid viscosity, which means it is independent of the fluid viscosity. The point is, here we have categorized, or this thing is categorized based on either the fluid density or the fluid viscosity. Now, you remember a dimensionless number that actually defines this importance of these two parameters, that is the viscosity and the density, or the density and the viscosity. It is nothing but the Reynolds number. Reynolds number defines the importance of the inertia force and the viscous force. High Reynolds number, inertia is high; low Reynolds number, viscous force is high. Now, you can relate that means in case of laminar flow, when we are saying laminar flow, the viscous force dominates. So, this part is basically the viscous force, and this part contributes in the inertia force. It contains the rho u square term, and here we have the mu term. So, which means this famous argon equation is having two parts. One is almost identical with the Koenig-Karman equation with a different constant value, and the other part is the Black-Balch-Plummer equation. Now, these constant values we will see when we will cover the multi-phase cases. This constant actually varies. This 150 and 1.75 are basically the empirically fitted constant values. Okay, like, because you have seen in the last class that when we mentioned that K3 depends on the shape and the surface property of the object, and it is numerically close to 5, that comes from several experimental values. We call these are the empirically fitted constant values, that you do thousands of experiments, you try to fit those experiments with a best fit curve, and doing so you come up with several constant that are the empirically fitted constant values. So, these are 150, 1.75, these are basically such values. Okay. Now, the point is friction factor. Okay. If you remember the friction factor in fanning friction factor, okay, in similar way or analogous to that friction factor, we can define the argon equation in terms of the friction factor as well, by defining the friction factor as this term. If you look at this expression, it basically forms that friction factor term in the fanning friction factor with the inclusion of this voidage parameter. And then if we define that argon equation is simplified to friction factor expression, which is nothing but 150 by Re star, which is the Reynolds number, or here the particle Reynolds number. Now, that particle Reynolds number is defined in this way, which is the diameter, superficial velocity, fluid viscosity, fluid density divided by the fluid viscosity multiplied by the 1 minus voidage. By defining the Reynolds number in such a way, it has been observed that the laminar flow condition prevails if the particle Reynolds number is less than 10. Okay. Strictly speaking, if it is near about 1, it is fully laminar. The transition region is from 10 to 2000, and fully turbulent region is when it is more than 2000. So, accordingly, this friction factor value, okay, also changes, because now you can understand this argon equation had two parts. One is the viscous force term, other is the inertia force term. Now, the viscous force terms becomes dominant in case of laminar flow, inertia becomes dominant in case of turbulent flow. So, in laminar case, the friction factor would be mostly contributed by this 150 by Re. Okay. And in case of turbulent, the friction factor value is a constant, which is 1.75. Eventually, this friction factor and the Rep in a log-log scale would look like in this way, that it will have a slope, okay, of 150 by Re, and in the turbulent region it is a constant value. So, that means that argon equation can be used for the complete flow regime, be it laminar or the turbulent, and we will see afterward that automatically one of the part becomes important in either in laminar or in turbulent cases. The contribution is more and more in the one of the cases we will see in when we will solve some problems related to this. So, this Argand equation you can use it irrespective of the flow region, and for this is specially mentioned here, it is for the spherical object or the spherical particles having a diameter of x. Okay. If the void is known, single phase flow when it is happening, you can calculate its pressure gradient through a mono-sized sphere, stack of mono-sized spheres. Okay. So, what happens in case of non-spherical particles? Although while developing this Koenig-Karman equation in the last class, if you have remembered, then you understand that we defined the generic values of the hydraulic diameter and etc. Okay. The point is that for the non-spherical objects, this Argand equation as well as the Koenig-Karman equations both can be used, okay, with the equivalent diameter by choice of a suitable equivalent diameter. Now, what does this mean by suitable term or the appropriate one? This appropriate one would be here that would have a diameter of a sphere having the same surface to volume ratio, because this is what, if you remember this development of Koenig-Karman equation, this is what was more important, that SV term, okay, that we converted the SB, which was the surface area per unit volume of the bed, to SV term, which was surface area per unit volume of the particles. Okay. So, basically our stress during the development of Koenig-Karman equations and in fact in this Argand equation is to have importance on the surface area per unit volume, this quantity. So, if there is a particle of irregular shape or it is non-spherical particle, then it is wiser or it is appropriate to have a equivalent diameter that will have a same surface area to volume ratio of a spherical object, which means the surface area of particles per unit volume of particles is what we are looking for and should be given the highest consideration. So, if we use the surface volume diameter here, now you remember the initial classes when we defined several types of diameter and we solved one problem related to this Argand equations, and we mentioned that during this solution of Argand equations, what could be the appropriate diameter. There was a mention of that what would be the appropriate mean diameter that we should choose while solving Argand equation of non-spherical particles. Now, here is the answer, that when solving such cases, either be it Koenig-Karman equation or the Argand equation, it's always you should put a stress on the surface volume diameter, which is the XSV in this case. How do you calculate that? You basically equate that surface to volume ratio of that irregular shaped body with the same of a spherical object, and you find out its diameter and use that diameter in this expression. So, the generic expression for Argand equation as well as the Koenig-Karman equation becomes this with the XSV term. This is the only change that has happened here, that is the equivalent surface volume diameter. So, if you have understood this concept, then we move on to one of the problems. Okay. Now, the problem says that there is water that flows through 3.6 kg of glass particles of density 2590 kg per meter cube that forms a packed bed of depth 0.475 meter, okay, and diameter of 0.0757 meter. Okay. The variation in frictional pressure drop across the bed with the change in water flow rate for a range of 200 to 1200 cc per minute is given in this table. We have to show that the flow is laminar, where this flow rate versus pressure drop data is given. We have to calculate the mean surface volume diameter of these particles, and we have to calculate the relevant Reynolds number. So, here the first part is that we have to understand this flow rate versus pressure drop value. We have water flow rate, we have pressure drop value, which means that there are glass particles. We form a packed bed of known depth, okay, and then water is flowing through that packed bed with a varying velocity or the flow rate. For each constant flow rate, we have measured the pressure drop across the bed, and these are the value that when there was a steady state with 2 cc per minute, 200 cc per minute of flow rate, we had 5.5 millimeter mercury pressure drop. Similarly, these are the value. So, at first we have to demonstrate that the flow is laminar. So, this is the first part. So, how do we do that? The point is, if you remember this expression, the first part of the Argand equation, okay, because you do not know initially that in which region this operation is happening. Okay. So, if we use Argand equation, the first part consists of this parameter, and again if you remember, this pressure drop was linearly varying with the flow rate or the superficial velocity here, which in other way we can say is the flow rate. The point here now, we have these two data. Okay. So, at first we convert this to the superficial velocity and the pressure in Pascal to be in a consistent unit. So, from water flow rate cc per minute, we at first calculate what is the superficial velocity. Okay. How do we do that? We have the flow rate q, we have the cross sectional area, that is the information given in the problem. Okay. So, from that we calculate the, for each and every flow rate we calculate the superficial velocity. From millimeter mercury we convert that to Pascal. Then if we plot this u versus pressure drop, okay, and if it gives a straight line, then it is established that this flow this operation is happening in the laminar region, because this is the point that this the first part of this Argand equation del p by h is linearly varying with the superficial velocity. So, we do that, we see that the superficial fluid velocity and the pressure drop, these are the points which we can fit through a straight line with a slope of 1.12 into 10 to the power 6 Pascal second per meter. That establishes the flow or the operation is happening in the laminar region. I hope this concept is clear, that if we plot the del p versus u data, the superficial data, and if it becomes a linear, then undoubtedly we can say this operation is happening in laminar region for a single phase case. Okay, and that slope value is nothing but this 150 multiplied by this parameter, because del p by h was of this one. So, if del p and u we plot, so it becomes 150 mu h divided by x p square multiplied by 1 minus epsilon square by epsilon cube. So, this parameter is basically the slope value. Now, if we go back to the problem again, now it has been asked that estimate the mean surface volume diameter of particles. Okay. So, which means we have to calculate what is XSV. Here flow is laminar, we have got the slope value is known, this slope parameter we have equated with the known value now. Now, here bed height is known, viscosity is known, the point here is the epsilon or the voidage. This information is directly not given in the problem statement. There is no mention of the voidage. Here the information are given is that the mass of the bed is given, the depth is given, okay, the diameter is given, the density of the particle is given, and the flow range is given here 200 to 1200 cc per minute. So, here then what we get is that mass of the bed is basically equals to the cross sectional area, okay, multiplied by the height and multiplied, so volume multiplied by the density of the particle. Okay, the volume is the cross sectional area multiplied by the height. Now, the cross sectional area for the solid particles is A multiplied by 1 minus epsilon, isn't it? Because epsilon is the voidage, 1 minus epsilon is what the solid fractions are. So, in a cross sectional area of A, the solid consideration should be A multiplied by 1 minus epsilon multiplied by the h, the height of the bed, that gives you the volume of the solid particle multiplied by the rho p is the mass of the bed. This mass of the bed is given, which is 3.6 kg. H is given, okay, the diameter is given. So, which means you can calculate all other parameter, or you can replace the all other parameter and calculate what is the epsilon. If we replace the numerics, we get this epsilon value of 0.3497. Okay. Now, if we replace this epsilon in this expression with the other known value of viscosity, because viscosity value is given here for the water, we know the viscosity value, and this height is also known. So, we get the XSV. Okay. So, here basically this epsilon is known, height is known, this m actually is not coming properly here, this is actually the mu. So, mu is 0.001 Pascal second. If we replace this value in that slope expression, we get what is your XSV, or which is the mean surface volume diameter of the particles, and that comes out to be 792 micron. The point was, the third part, what is the relevant Reynolds number? Okay, this is also to verify that whether our the assumption of only consideration of the first part was valid or not, but here there was no assumption in fact, because we had this data. In other problems, when we solved that, we assumed that this is the laminar condition and then solved the problem. Here the point was, all the data points were given, the experimental results were given. So, there is no point of any verification of the Reynolds number, but we had to calculate what is the Reynolds number, and with the highest velocity from this table, if we calculate the Reynolds number from the definition of the Reynolds number, this x, considering x now is the 792 micron, u is the superficial velocity, rho f of the fluid, mu is the viscosity of the fluid, 1 minus epsilon is the 1 minus voidage. We find that it is 5.4, which is well within the laminar flow range. Okay. So, this feat, in fact, this feat with a straight line also in other way it is justified, that indeed it should fall in a linear relation. So, the takeaway message from this whole class today is that we have to look for this Reynolds number range, okay, and it's then that actually will help us to understand that which part will be dominant in argon equation. The argon equation encompasses both the flow regime, that is the laminar and the turbulent flow regime. Okay, it is the combination of Koenig-Kármán and the Bach-Palmer equation. It can be also written in form of friction factor, where 150 by Re plus 0.75 is the relation, and the friction factor becomes only 150 by Re in case of low Reynolds number, that is beyond below 10 in case of laminar region, that is in case of turbulent region it is 1.75 or a flat profile. If you remember this graph, then it would be easier. This again, this is not act to the scale, but this is the schematic. Okay. For the non-spherical particle, both these equations like the Koenig-Kármán, Bach-Palmer as well as this overall argon equation can be used with the surface volume mean diameter, and then a problem we have seen with the surface volume mean diameter, that how it is useful. So, with this I will stop here, and we will come back with the next class, and till then I hope you are enjoying this class, and thank you for your attention.